Today's background is from Lightning Ridge, which is a small town if you take the New South Wales-Queensland border and go halfway along it and come south. It's a town that exists for opal mining. It's the main reason people live there. It's the main reason people go there for tourism. But one of the nice features of it is it sits on the edge of what's known as the Great Artesian Basin, which is a very large subterranean aquifer that extends through Queensland down into South Australia and New South Wales. And if you sink a bore down to this aquifer, you can bring up rather hot water. And if you mix it with some cold water and put it into a concrete tub, like the one you can see just here, you have quite a nice place for a swim. And there's a bunch of these, they call them bore baths, dotted all over northern New South Wales, Moree and Burren Junction and Lightning Ridge and a few other places. And I like this one particular because A, it's free, B, it's open 24 hours a day, and C, it's the only one I've been to that's genuinely hot, in the sense that you don't want to spend too much time in the water because you feel uncomfortable after a while. And one of the nice aspects of it is that you can rock up at 5 o'clock in the morning and watch the sunrise. And if you do that in winter, it's 0 degrees out in the air and 43 or 44 degrees in the water. And you can sort of have a nice swim, sit out in the air and cool off and alternate until till the sun comes up, and then you decide to go about the rest of your travels for your day. It's one of the sort of nice ways to spend a morning in New South Wales. So if you're nearby, definitely worth a look. In this second half of Lecture 9, I want to look at operators and eigenvalues a little bit more closely now that we've shifted from sort of the vector approach to dealing with systems with a very small number of observables to the functional approach for dealing with systems with a very large number of observables in quantum mechanics. The last lecture was a pretty big conceptual jump from vectors to functions. And so in thinking about that, I want you to be a little bit kind to yourself. At first, it will look like it doesn't make sense, and there will be lots of aspects that are just very difficult to come to grips with. I want you to accept that at first. If you just go, I'm never going to get this, I should just give up. That's not the right way to go. What you want to do is basically try to distill down all the things that you don't understand into questions that will enable you to understand it and get those questions answered, because that's the pathway from working through from I don't get it to I get it. And it's a really useful thing to get, because once you sort of have this concept working properly in your head, the rest of quantum mechanics becomes a lot easier. And in particular, the way that notation gets used becomes a lot easier, because in a lot of books, people slip into this mindset of mixing vectors and functions. And if you come from either of the approaches alone, it looks very weird. But once you understand that bridge across, you can kind of see, how the two pictures fit together and how to make things work. Okay. And so what you're going to notice as we go on from today, I'm mostly going to deal with functions in the maths in this second half. But as I roll out into next week, you're going to start seeing things where I have little bits of maths that look like vectors, little bits of maths that look like functions. And really, it's all underpinned by this idea that we can continuously move between the two. Okay, so let me bring up some slides. You'll remember in the earlier parts when we dealt with spin that for every observable of the system, we would have an operator. So for example, we were interested for our electron in what the Z component of the angular momentum was, whether the spin points up or down. And we had a mathematical operator for that, which was the thing called a Pauli matrix, a 2x2 matrix called sigma Z. Okay, and what it did was it acted on vectors to give you new vectors. And the reason why we're interested in it was for things that are eigenvectors of that operator and what the corresponding eigenvalues were. The same thing happens when we come across to functions. We've just got to think about it in a slightly different way, okay? So at the moment, we're taking as our model problem a 1D line with a particle that's traveling along that line, and at any point in time, it can have some position x and some momentum p. Okay, and we're usually just interested in measuring either X or P or both sometimes. And we'll talk what happens when you try to measure both when we get into the lectures for next week. There's mathematical operators connected to both of those things. A measurement of what the position is, so where along the x-axis it is, and a measurement of the momentum along the x direction, which we usually call px, just to distinguish it from when we go back to 3D, moving along y and moving along z. Px, which is how fast it's moving or how much momentum it has, because we combine mass into momentum, of course. How much momentum it has along that x-axis. And those two things are given by operators that I've shown just here. So the operator for position x is actually rather simple. All you do is just drop in a variable x. It's what we call a multiplicative operator, in the sense that it just drops in and often you can move it around. And then the operator for momentum will look a little unusual at first. It's basically minus IH bar d on dx. It's what we call a functional or a differential operator. And so what it does is it takes whatever it's operating on and takes the derivative of it. So unlike a multiplicative one where you can sort of move it around with too much trouble because it multiplies things, the differential operators really operate on a function, and so moving them to somewhere else is a very big change because they will operate on something else rather than the function you want them to operate on. Okay, we'll talk a little bit more about the care that you have to take with where you position operators as we get into next week and look at commutators. And those of you interested in where and why there's a minus I out here, I've left this as an exercise for this lecture. You can look at sort of the Hermitianness of operators. So you remember that we have the requirement that operators are Hermitian in quantum mechanics, in the sense that if you take the conjugate, it's equal to the operator. In this operator P of x here, the minus I that's out the front basically serves to make that operator Hermitian. Okay, and I'll let you look separately in my exercises for this lecture for some maths where you can sort of walk through seeing why that is and how that's the case. Okay, so in much the same way that operators act on a vector to give you a new vector, operators act on a function to give you a new function. And what we're often interested in for some arbitrary operator L acting on some arbitrary function f of x is what we call the eigenfunction and eigenvalue. Okay, and so if L operates on f of x and what we get back is that same function multiplied by a complex number, lambda, then that function f of x is an eigenfunction of the operator with a corresponding eigenvalue lambda. Okay, so all we're really doing here is taking the idea of eigenvectors and eigenvalues and transferring it across to having eigenfunctions and eigenvalues. One thing that you'll notice is I'm going to start slipping into some wording now and I will be interchangeable about it, and I will be interchangeable about it because I think interchangeably about it. So there will be three words that I will use more or less interchangeably probably for the rest of my part of the course. It will be eigenstate, eigenfunction, and eigenvector, right? So you'll remember that vectors represent states in the system. An eigenvector is, as we saw earlier on, basically a basis vector. It's one of the observable states of the system. And so an eigenstate and an eigenvector are kind of the same thing, right? If we think about an eigenfunction now, an eigenfunction is like an eigenvector. And if you think about just running continuously from functions to vectors and that being perfectly okay in quantum mechanics, in some senses, an eigenvector, an eigenstate, and an eigenfunction are all the same thing. It's just different versions of the name and different ways of thinking about it. Okay, so if I say eigenfunction, I mean a function. If I say eigenvector, I mean a vector. If I say eigenstate, I could mean both. And sometimes I might even say eigenfunction when I really mean eigenvector. And you'll all know, because we can make that jump from one to the other, it's perfectly okay to do it. Okay, and the eigenstate, eigenvalue, eigenfunction thing, all of those are connected to eigenvalues, right? So there's an eigenvalue for an eigenvector, there's an eigenvalue for an eigenfunction, and there's an eigenvalue that's sort of connected to an eigenstate, because the state is either of those. And so you sort of keep these together, right? And the eigenvalue is an eigenvalue in all of those cases simply because it's just a complex number that sits out the front for something that's either an eigenstate, eigenfunction, or an eigenvector. All right, you'll get used to the way it uses as we work along. So what I want to do is just look at what the eigenvalues and eigenfunctions for the position and momentum operators are in this half, so that we can start to get a look at how these operators work from a functional perspective rather than from a matrix perspective. And so what I'm going to do is start with x first, because it's the simplest of the two operators. And what I'm going to do is start with the Eigen equation for a particle that has a very specific position, x equals x naught. So what would happen is we would act the operator x on the state. Okay, so usually for functional operators, we have a little hat on them. That's the way that you tell that they're an operator. We have x hat acting on the state psi, and what it will give us is our state psi back. So basically our state is an eigenfunction or an eigenstate of a measurement, and it will pop out a corresponding eigenvalue, and that eigenvalue will be I am at position x naught. Okay, so we have this as our Eigen equation. Let's bring up some paper. X hat acting on the state psi is equal to x naught psi, like so, right? And you'll remember in the last lecture where, actually it's still up on the screen here, where if we look at a very specific eigenvalue against that state, what happens is we get up orthogonality relation that basically picks out that particular eigenvalue out, okay? What it also does is picks out that particular state. So the way we can write this directly is, rather than as the state psi being the sum of all of the possible, or the linear combination of all the possible eigenvalues for position, it will pick out the particular position that we're interested in. So what we would really be writing here is x hat psi of x is equal to x naught psi of x, okay? All we're really saying here is if we're at position x naught, we will get a wave function that corresponds to us having the particle found at that position x naught. And I'll show you a little bit further down this line of algebra how this connects into both the Dirac delta function and the ability for the Dirac delta function to pick up states. It'll be your first look at it, so if you don't get it, keep playing with it, you'll get there. Okay, so we have this basically as our Eigen equation now. And we can do something quite simple here, which is to basically say that the operator x acting on that state is really just multiplying it by x, right? So if we go x hat psi of x, it's really just multiplying x by psi of x, okay? So this here is just an Eigen equation. This is action of the operator. And those two, the right-hand terms on those two equations are actually going to be equal, right? Because the left-hand term is the same. So what we're really saying here is that x psi of x is equal to x naught psi of x. And we could write this as x minus x naught psi of x is equal to 0. Okay. What this means is, again, we've got this idea of if we multiply two things together to get 0, one of them has to be 0, okay? So there's two possible outcomes. The first is that if x equals x naught, then x minus x naught will be equal to 0, so psi of x can be not equal to 0. In other words, at the position x naught, the probability of finding the particle is not zero, or if x is not equal to x naught, then x minus x naught is not equal to zero. Therefore, psi of x must be equal to zero. And what that says is if we look anywhere other than the position x naught, our wave function has to be zero. In other words, the complex prefactors that give us the probability have to be zero, and we won't find the particle there. Okay? So all we've really done is by finding that the state of the, or the wave function for the particle is an eigenvalue of, or an eigenfunction of the operator x, is more or less just to identify a particular position, right? Now, one thing we need in here if psi of x is not zero is that we need it to be normalized. And so one function that we know of that is zero everywhere and not zero at a specific point that is actually normalized is the Dirac delta function that I showed you in the first half of the lecture, right? So what we tend to do here is basically say that our wave function here is delta x minus x naught, which is essentially a delta function such that it's zero everywhere except for x equals x naught, where it's infinity, but the integral of that curve over the entire range is 1, so that what you're really saying is that the probability of finding the particle out here is 0, and at the position x naught, the probability of finding the particle is exactly 1. Okay? This is sort of why the Dirac delta function is important. It basically becomes the wave function for a particle at a specific position when we build our mathematical model here. Okay, so one thing I want to consider just following up here is what the inner product of some arbitrary position state and a position eigenstate x naught would be, right? Let's write this down for a second. Psi and x naught, right? So what we would be writing here is, for example, x naught and psi. What we're really doing here is going our state psi, if you think back up to the version of it that we have up here, is essentially the sum of all the possible eigenstates, right? So we're now going back to the idea that our state psi is essentially an entirely arbitrary position for our particle along the axis. It could be anywhere we like now. And we're looking for the inner product of that with a very specific position x naught, right? So what we're really doing in some senses is taking a state. If you think back to our single spin, we would have some state A, which was some superposition of our basis states up and down, and project it onto the up in order to work out what the probability of getting up is. What we're doing here, in a sense, with this inner product is going, we've got a state that's the superposition of all the possible positions that we could have. So essentially the particle could be anywhere and we don't know where it is. And we're going to project that onto the basis state corresponding to an observation of the particle at x0, which would be the state x0. Okay? You can imagine taking the product of this and its complex conjugate and getting the probability of finding the particle at some particular position. So let's work this through. This is going to be the integral of the wave function for finding the particle at our position x naught times the wave function for finding our particle at position x, right? So we've got a wave function for our particle at position x naught and a general wave function for our particle as a function of x. And you can imagine this be like multiplying two vectors together, one of which is just, your 1, 0 state for an up, and the other one would be your arbitrary state A, which would be, say, alpha up and alpha down, okay? But now taken to infinite number of dimensions, so we have to add across these two separate functions, one of which has the probability of the particle at one point, one of which has probability of it being anywhere because it's arbitrary, right? So, and we need a dx. And then this just to be clear, this would be minus infinity plus infinity, so we'd look across our whole space. This thing would be integral. We just worked out what our wave function would be for our particle at a position x naught. Okay, so we could just call this x naught up there just to be more specific. So this would now be delta x minus x naught. And of course, this one on the right is going to be a bit more arbitrary, so it's psi of x dx. And you'll remember from our definition of a delta function that integral from infinity to minus infinity of delta x minus a of f of x dx will give us f of a. So this thing just up here, if we just jump a line down here, will be the function psi of x, because this is the equivalent of that function there. X naught is the equivalent of a just here, so it will end up being that function psi at x of naught. Okay, we can take this relation x naught psi of psi and x naught, and we can do something that's really common in physics, which is to generalize it. Okay, so what we can say is we don't care necessarily about x naught because the exact same relationship would hold for a position x1, or it would hold for a position x2, or it would hold for some position, you know, x minus 1 or whatever you like. And so what we can do is just get rid of that label, right? And so we could write this more generally as x psi equals psi of x. And so what we're really saying here is that the wave function psi of x, which you've probably heard of in your first year courses, and if you haven't, if you've done some reading in quantum mechanics, you've probably seen it as well, is really just the projection of the state vector onto the eigenvectors of position, right? What this really is this thing here. This thing is a specific position, and this is an arbitrary state. So it's the equivalent of, for a spin system, taking the projection of some superposition of up and down onto up. And in much the same way, it's taking some arbitrary position for our particle, because it would be the sum of all the possible eigenvectors, and taking the inner product of that of a specific position to work out what that is. The value of that wave function at any particular point is basically just what that inner product is. So at the end of this, what we basically have is a definition for our wave function psi of x that we can see as one of two things. It either corresponds to the inner product between the arbitrary state of the particle, so any position we like, and one specific position, or as a Dirac delta function that is centered on the position of the particle, okay, which basically just means we won't find the particle anywhere that the particle isn't, and we will find the particle at the point where the particle is, okay? This is something we call the position representation, and I will come back to what we mean by position representation after we do the momentum operator. So let's switch over to the momentum operator now. What we can do here is start in exactly the same way by looking at the Eigen equation for momentum. So what we're basically saying as an Eigen equation is the operator P acts on the state psi, and it gives us back the state psi multiplied by a number, and that number ends up being the momentum of the particle, okay? So let's carry that down onto our notes. P acting on psi is just P on psi. And we also have a form already given to us for this momentum operator, which is minus I h bar d on dx. And you'll see this sometimes written as d on dx. Sometimes you'll see it right in del on dx, del on del x in terms of partial derivative. Those two, in most cases, are more or less interchangeable, and you'll see the textbooks will switch between the two. Sometimes you need to be careful about whether it's a partial derivative or not, but for the most part, you sort of switch between the two somewhat ambiguously, and you'll notice that all the books do it, and my notes will also to some extent do it. So let's apply the operator to that function. So what we'd have here is p hat psi would basically be minus I h bar d on dx on this state psi. And what we're going to do here is same game we played last time. We're actually going to make the right-hand sides of the Eigen equation and just acting the operator equal to each other. So this will mean we've got minus I h bar d on dx of psi is equal to p psi. And I'm using the hat to denote operators in here and being quite careful about that. So at this point, we can do two things. One, we could go back to our original state for psi. So it would be sum over I of psi of x and all of our states x, right? It would look something like psi is equal to sum over I psi of x x, like this, okay? And you can do all of the maths with that in place. But one of the ways to make this easier for just notation here is just to assume that what we're going to do is have the particle in some fixed position at the moment, which is some position x, and just deal with psi of x, the wave function for that position. Okay, if I'll let you check with the sum state for yourself. It's just a little bit more in the algebra that's distracting, and that's why I want to remove it. So minus I h bar d on dx psi of x is equal to p psi of x. Okay, so we're just picking out a particular position for the particle at the moment. What we can do here is multiply both sides by I. And so if we do that, minus I times I will be equal to 1. So this side will be h bar d on dx psi of x is I p psi of x. And then we can divide the h bar across as well. So d on dx psi of x is equal to I p on h bar psi of x. This thing here is just a differential equation, right? You've seen this one before, hopefully either in your maths courses or in your earlier physics courses, and it has a very well-known solution, psi of x. And I'm just going to put a little p down here just so that we know that this is now the solution to a differential equation rather than just an arbitrary wave function. Okay, so this is just to remind us that this particular thing we're getting is an eigenvector corresponding to the eigenvalue p in this Eigen equation up here. Okay, it's going to be a e I p x on h bar. And let me just quickly verify this as a solution. If we do d on dx of psi p of x, it will be d on dx of a e I p x on h bar. And of course, you know, when you do the derivative on this, you basically just pull a copy of the exponent down. So it will be I p on h bar. You're taking the derivative of IPX on h bar, so the x will disappear. AEIPX on h bar just here. And this, of course, is IP on h bar psi p of x. Okay, so that thing is a solution of the differential equation, and hopefully you've done that before in other courses. This thing A out the front here is just a normalization. And I'll let you show this for yourself as an exercise, but if we normalize this thing, what we end up with is psi p of x is equal to 1 on 2 pi e I p x on h bar. Okay, the normalization for that is not quite as trivial as it might initially seem, because you're actually dealing with taking an integral, as we saw just before, of that function and its conjugate, and that ends up making the prefactor popping out a little bit tricky because you actually need to then solve that integral, right? But I'll leave it as an exercise, as a fun one to chase up. One thing that you'll notice in here is that this thing here is actually a wave, right? If you think back to first year, you will have seen waves as e to the I kx minus omega t, where k is 2 pi on lambda and omega is 2 pi on the frequency. No, it's 2 pi times the frequency. Sorry, 2 pi times the frequency. And so what we can do is see this thing up here as a wave, and we can see this as a wave where k is equal to p on h bar. All right, let's think through just for a second logically what this thing is. Lambda is equal to 2 pi on k, just taking this expression just here. And so it will be equal to 2 pi, the inverse of k is h bar on p, like so, okay? And now we can solve this thing for p. So p will be equal to 2 pi h bar on lambda. And of course, we know that h bar is equal to h over 2 pi. So this will be equal to 2 pi on lambda h on 2 pi. The 2 pi's cancel out. This thing is just h over lambda, which is just the de Broglie wavelength that you'll know from your first year physics courses. And so this is kind of interesting. What's just suddenly popped out here is we really just said, oh, you know, what we're going to do is we're going to go from angular momentum as a two-spin system up and down, take vectors, extend the idea up to deal with functions. We now have functions. What we're going to do is apply that to a particle having a position and a momentum. And we're going to have operators for these. The form of the operator here is actually kind of simple, right? It's really just a derivative. All it is it takes a derivative. We multiply by h bar. H bar is a constant that turns up all over the place, right? If you think back to your electron spin, the angular momentum components are plus h bar over 2 and minus h bar over 2 in much the same way. And then there's a minus I out the front, and that minus I out the front is really just there to make sure that that operator is Hermitian. And if we bring all these things together, all of a sudden we get something that basically tells us that our wave function has to be a wave, and it has to be a wave in a sense that the momentum is tied to the wavelength that we get for that wave function. Okay, so there's not really anything special that we have to bring into quantum mechanics of you know, we must make this thing a wave. In a sense, it really just pops out of the maths. And the interesting thing is that if you consider this form for the momentum operator and you consider what the sort of kinetic energy looks like, you realize that that is the form that it should have on the basis of what kinetic energy should look like. I'll actually put a note in the exercises, a new note in the exercises on this, so that people who are curious about it at this point in the course can see where this comes from. Okay, but the nice thing here is we've got eigenvalues and eigenvectors of momentum, and basically what we show is that we end up quite simply with the momentum being connected to the wavelength just popping out of the maths for us. Again, it's one of the nice things about this approach to quantum mechanics is a lot of the things that turn up in quantum mechanics are not concepts that are just made. They exist simply because we live in a world where maths is the way that maths is, and these things are natural consequences of mathematics applied to physical problems. So there's one last place I want to finish up here, which is to talk about this idea of position representation again. You'll notice that we just arrived at a wave function that is a eigenstate of momentum with an expression that looks like this, okay? And it is a function of x in here because it says it's a function of x. There's a momentum tied in there. And again, we've got this sort of position representation written up. We'll get into this as we get a little bit further into next week. When we think about our particle on a line, what we've got to do is come back and think very briefly about what our bases are, okay? So if you think back to your single spin again, you have a single spin, and what you can do is you can ask the question, is the angular momentum along Z? Or you can ask the question, is the angular momentum along X? And those two things are distinctly different measurements, right? This is a measurement along Z, this is a measurement along X. There's two different outcomes, up, down, and left, right. And what we find is that those are two different bases for the same vector space that you have. So your up down would be like this, your left right would be like this, and if you do a change of basis to think of the other one, you're basically just rotating that basis by 45 degrees. Okay. If we now come back to our particle along the line, our position x is essentially something that we can measure. And it's something we can measure with an infinite number of eigenvalues. Okay, so essentially what we're dealing with is an infinite dimensional Hilbert space where every single eigenstate in here corresponds to a separate orthogonal basis vector. Okay. An observation that you can make that would be in the same infinite dimensional space is what is the momentum, okay? And that momentum, again, has a whole pile of possible eigenstates and eigenvalues for that momentum. And those are also orthogonal states in your infinite dimensional Hilbert space, but they're actually just a separate basis in that same space, okay? So one thing I want to point out at this point is that you can't really write states that look like this, where what you're saying is that the state is basically the sum of all of the eigenvalues for position and all of the eigenvalues for momentum, and you can treat those as sort of, you know, separate things that you all build together in one linear combination. That ends up being physically wrong, and it ends up being incorrect ultimately because of something we'll talk about next week regarding simultaneous observables, which is that there's an uncertainty principle between x and p of x. And what actually happens is that x is one basis for the same space that the particle's in, and another basis for it is our momentum basis. And so when I talk about position representation, what I'm saying is we're working in the basis of thinking about x. And as you know, back to our sort of single spin, you can still, when you're working in the up-down basis, do things with right and left. You're just working in the up-down basis. And it's more or less the same here. If you're thinking in terms of the basis as vectors as your sort of eigenfunctions or eigenvectors for position, you can still work with momentum. You're just now writing it in terms of the eigenvectors for position. You can make a basis change in much the same way that you can with your spin system to thinking about momentum instead, okay? And this is something that we call the momentum representation. And there's an equivalent version of this where you write the wave function in terms of p, you have your state in terms of p, and you sort of transfer between one and the other by essentially executing a basis change. I don't want to go into that too deeply at this point. I'll let that come together in the second half of the course when you start to look at the sort of Fourier transform connection between position and momentum in the functional version of quantum mechanics. I just want to point out that you have to be really careful here in terms of thinking about position and momentum in this sort of functional aspect. Because they're actually separate bases. And so most of the time what you'll see, actually you operate in this position representation, and that's why if we go back a slide for a second, you'll notice that the wave function has a slightly complex form here. It's because we're writing it in the position representation rather than in the momentum representation. If you take both of those functions for, you know, eigenvalues and eigenvectors of position and eigenvectors and eigenvalues of momentum and transfer the space, the momentum ones look easy and the position ones look difficult, okay? In much the same way that when you switch between your up-down basis and your right-left bases, whichever is the predominant basis looks easy, and whichever is the other basis looks more complicated, okay? I think I'll finish there. Where I'm going to go next week is taking these ideas and starting to build up the uncertainty relation that you see delta p, delta x, so that you can see that also pops out logically, more or less just starting from this original idea of having a spin up and down and thinking about how that works in a linear algebra mathematical framework. I'll see you next time.